Hello everyone. Today I would like to present our project titled DC Motor Speed Control Theory and Design Review. This project is brought to you by Peninsula Tasmali and Timor. This project focuses on modeling, controller design, simulation, and performance analysis of a DC motor control system. The main objective of this project is to model, simulate a DC motor speed control system using MATLAB and Simulink. Different controllers, including lag, lead, and PID controllers, are designed and compiled to evaluate system performance, stability, and steady-state accuracy. So, what is a DC motor system? A DC motor is an electromechanical system that converts electrical energy into rotational motion. In this project, the motor speed is controlled by adjusting the armature voltage. So, the input is voltage and the output would be the motor speed. The figure in this slide shows the electrical equivalent circuit and the mechanical model of the DC motor. On the left side of the diagram, the armature circuit contains the resistance R and inductance L, which affect the motor current. The applied voltage drives current through the circuit. The symbol E represents the back electromotive force or back EMF, which opposes the input voltage as the motor rotates. On the mechanical side, J represents the rotor inertia and B represents the damping or friction coefficient. These parameters affect the rotational motion and dynamic response of the motor. Overall, this diagram represents the relationship between the electrical input and the mechanical rotational output of the DC motor system. The DC motor is represented using a transfer function model, which is Gs equal to K over Gs plus B multiplying Ls plus R plus K squared, which describe the relationship between the armature voltage input and the motor speed output. The parameters include inertia, damping coefficient, resistance, inductance, and motor constant. Now I will explain the simulink model used in this project. This model compares 4 different DC motor speed control systems. The first rule is the open loop system, which means the DC motor is connected directly to the input signal without feedback control. The second rule uses a lag compensator. In this closed loop system, the output speed is fed back and compared with the reference input. The lag compensator is used mainly to improve steady-state performance and reduce steady-state error. The third rule uses a lead compensator. This system also uses feedback control, but the lead compensator is designed to improve the transient response, especially response speed and stability behavior. The fourth rule uses a PID controller. The PID controller combines proportional, integral, and derivative actions. It is used to improve response speed, reduce steady-state error, and maintain a stable output response. All 4 outputs are connected to max blocks, so the responses can be displayed together on the same scope. This allows us to compare the open loop response with the control responses clearly. The output is also sent to WASP block, which exports the simulation data back to MATLAB for further analysis and save it into MAT file. This shows the internal DC motor subsystem model. The model is divided into 2 main parts, the electrical subsystem at the top and the mechanical subsystem at the bottom. In the electrical subsystem, the input voltage is applied to the armature circuit. The resistance block represents the armature resistance, while the inductance block represents the armature inductance. The back electromotive force represented by Ke acts as negative feedback opposing the input voltage. The signal then passes through the integrator block, which calculates the armature current. In the mechanical subsystem, the motor torque is generated using the torque constant Kd multiplied by armature current. The damping block represents mechanical friction, while the inertia block represents the rotational inertia of the motor rotor. Another integrator block is also used to calculate the angular speed of the motor, which becomes the final output of the system. Overall, this system combines the electrical and mechanical dynamics of the DC motor to create a complete physical simulation model in Simulink. Moving on, I will run the simulation and show how the scope displays the response curves for the open loop, lag, lead and PID control systems and the stability and frequency domain analytics. First, this is the pole zero map. The pole zero map shows the locations of poles and zeros in the S-plane. In general, for a continuous time system, if the poles are located on the left side of the X-plane, the system is stable. From these graphs, the poles are located in the left half plane, so the open-loop motor and the control systems are stable. Next, this is the Bode plot. The Bode plot shows how the system responds to different input frequencies. It includes the magnitude plot and the phase plot. The magnitude plot shows gain behavior while the phase plot shows phase shift. Finally, this is the gain and phase margin analysis. Gain margin shows how much the gain can increase before the system becomes unstable. Phase margin shows how much additional phase lag the system can tolerate before instability. Since the controllers have positive phase margins, the system have stable feedback behavior. Overall, these graphs support the step response results. They confirm that the design controllers improve the DC motor system performance while maintaining stability. Now let me explain about the step response effect on our different controllers. This graph compares the step responses of the open loop system and the control systems using lead and PID controllers. The yellow curve represents the open loop system. We can see that the output cannot reach the reference value and settles at a much lower value, resulting in a large steady-state error. After applying feedback controllers, the system performance improves significantly. The green curve represents the lag compensator. It improved the steady-state performance and reduced the steady-state error, although the response speed is relatively slower. The blue curve represents the lead compensator. This controller provides the fastest transient response and reach the reference value quickly, but it introduced a slightly higher overshoot. The orange curve represents the PID controller. The PID controller provides a stable response with very small overshoot and almost zero steady-state error, giving the best overall balance between response, speed, stability, and accuracy. So, overall, the results show that feedback controllers greatly improve the performance of the DC motor system compared to the open-loop response. In conclusion, this project successfully modeled and simulated as DC motor speed control system using MATLAB and Simulink. The results showed that feedback controllers significantly improved the system performance compared to the open-loop system. Among the controllers, the PID controller provided the best overall balance between response speed, stability, and steady-state accuracy. Overall, the project demonstrated the effectiveness of controller design and MATLAB Simulink integration in control system analysis. Thank you for your attention.